All right, let's try some of these practice problems. Remember, these are associated with sample problem A in chapter 3. So make sure that you go through sample problem A first. Okay, take note of what's going on in the sample before you try these practices. But once you do, obviously try these practices. All right, so the first thing we want to do is take note of what information the question has given us. Second, we're going to want to draw some sort of representation of that data so that we can wrap our head around what we're being asked to do. So, practice problem 1. A truck driver is attempting to deliver some furniture. First, he travels 8 kilometers east. And so we're going to represent our first delta x, because this is what we're being told is happening, 8 kilometers east. Remember, displacement is a vector quantity. It involves both magnitude and direction. We can also represent this appropriately as negative, typically on a four quadrant coordinate system, typically east, south, west, north. So this would, be a positive 8 kilometers because we'll be traveling east. Now, again, this is a convention. If you wanted to define your coordinate system a different way, you're more than welcome to do that. However, you're going to have to actually define it. You'd actually have to come out and state that first, because that's pretty much an extra step, and not a lot of people want to be that imaginative because, well, it doesn't really get you much. You can feel free to use a coordinate system, or you can use sign conventions. Then we read that he turns around. Okay, so, kind of taking an about face, and travels 3 kilometers west. Okay, so we have our second delta x, which is going to be 3 kilometers west, or again, as we've defined on this typical coordinate system, this could be negative 3 kilometers. Finally, he turns again and travels 12 kilometers east. Okay, 12 kilometers east. Again, as we've defined on this coordinate system, that would be positive 12 kilometers. Now, this might seem like a bunch of extra steps that you don't necessarily have to do. And in fact, I'm sure a lot of you don't have to do this. That doesn't mean, however, you won't benefit from doing exactly that. Okay, so this is the data that we are being asked to use. What are we being asked to do with it? Part A asks, what distance has the driver traveled? Now pay attention to this word distance, because this is a scalar quantity. That means only magnitude, no direction. Okay, so basically how many steps has this person taken? Okay, not their overall displacement, which would be a vector quantity. Means that you would have to take into consideration which direction the person was traveling. But this says distance. So scalar, meaning we're just going for magnitude. So what we're going to do here is take these values, but ignore the direction, because scalar quantities don't involve direction. So we're going to take the absolute values of these displacements, meaning just their magnitudes, and add them together. So this overall distance, just to represent it appropriately, is going to be delta x plus delta x1 plus delta x2 plus delta x3, which we know is 8 kilometers plus 3 kilometers plus 12 kilometers. And you're going to have to use a calculator or do that in your head if you want to. That's going to be 23 kilometers traveled. Now again, notice there's no direction here, just the magnitude. So in B, we get the other question. What is the total displacement? So this is a vector, which means we need magnitude and direction. So here, we're going to do essentially the same thing here, but include direction. So that means we're going to be using these sign conventions when we do our addition. So again, I'm still going to be using, I'll go ahead and write it down, displacement here. So actually, might as well use the appropriate symbol. And I'll go ahead and represent that as a vector quantity. Remember having a little arrow above your symbol indicates that it's a vector quantity. If you can't bold it yourself, if you're typing, just Control B to make it bold. But since I'm not typing, I'm going to draw a little arrow over the top of it. That simply indicates that it's a vector. So I'm going to add the vector of delta x1 plus the vector of delta x2 plus the vector of delta x3. So what does that end up being? A positive 8 kilometers plus a negative 3 kilometers plus a, again, positive 12 kilometers. Now, when I add these things up, I actually come out with 17 kilometers. What we really need to pay attention to here is how the questions are worded. Part A is asking about a distance traveled. That means it's a scalar quantity. You're not including direction. Part B is asking for displacement, which is a vector quantity. So there's magnitude and direction. And so that tells me to include something to give me direction. Here I'm using sign conventions. Okay, so make sure you're paying attention to how the question is worded so that you know exactly what you need to do. All right, still working on sample problem A, or at least the practice problems associated with sample problem A. Let's try practice problem number 2. While following the directions on a treasure map, a pirate walks 45.0 meters north. Okay, so I have, again, using the traditional 4 cardinal directions coordinate system, right? That helps me assign sign conventions and therefore directions. Going 45.0 meters north. And then turns and walks 7.5 meters east. What single straight line displacement, again, displacement, magnitude, and direction, it's a vector quantity, could the pirate have taken to reach the treasure? So what we're being asked here, what is the resultant? Okay, what is the resultant? So in order to find the magnitude, remember, displacement is a vector quantity, both magnitude and direction are required. I'm going to use the Pythagorean theorem, and then to find the direction, I'm going to use inverse tangent. Okay, so I'm going to have to do 2 things here. First up, I'm going to find the magnitude using the Pythagorean theorem. I can say that my resultant, okay, the magnitude of the resultant is going to be equal to the square root of my delta x squared plus my delta y squared, okay, which is the same thing as the square root of 7.5 meters squared plus 45.0 meters squared. Okay, so I'm writing down my equation again as the Pythagorean theorem just to make sure that I have my setup correct. And then I also like to write an equal sign showing the instructor or whoever's trying to give me points, the extension of that by plugging in my actual values. Now, once I get some action with my calculator, again, I'm going to go step by step, right? So we're not going to skip any calculator steps here. I end up with 56 meters squared, right? Because 7.5 squared is 56, but meters squared is meters squared, right? Because we're also squaring the meters. And then I have 2,020 meters squared. They have like units, so I can add them together, obviously, and I end up keeping the radical for now. 2,080 meters squared. Now simply plug that into calculator, square root it, and I end up with 45.6 meters. Okay, so that's only the magnitude. I still have to do the direction. And so basically my angle, and I'll use theta to represent that, is going to be the arc tangent. Okay, again, tangent, opposite over adjacent. So this is the angle I am using. Because remember, the pirate, yeah, it's a pirate here, the pirate walked north, then east. We're being asked if they just took one straight line, right? How could they change that and just get there in one straight line? Well, it means they'd have to tweak their direction by this angle, right? That's how I know not to use this angle or this angle, using this angle. So based on this angle, opposite over adjacent, again, not doing this in my head. I'm definitely using the calculator. I end up with, again, you have to use the appropriate number of significant figures because my calculator told me something like 9.456 and a whole bunch of gobbledygook that isn't significant, so I can't use it in my response. But using the appropriate number of significant figures, right? This has two significant figures in it. I'll go 9.5 degrees. Right, here's north. This is 9.5 degrees east, right? Because east is that way. East of north. So that single straight line, the total displacement of that line would be 45.6 meters east of north. That's the complete answer. On to number 3 in the practice problems associated with sample problem A. So here we have Emily passes a soccer ball 6.0 meters directly across the field to Kara. Is it Kara or Kara? I don't know why I'm asking. I don't care what you think. So 6.0 meters directly across the field. So the question is, what way should we orient the field, right? We still have a coordinate system to deal with because we do have to draw our representation. Now, just the way that comes to mind, for me, you can actually do it the other way around. It's totally legit. You just kind of have to flip some of the numbers. But I'm going to assume that the field plays, up and down, right? And then so when we say across the field, that means sideways, like sideline to sideline. So Emily passes the soccer ball 6.0 meters directly across the field to Kara. Kara then kicks the ball 14.5 meters directly downfield. Okay, downfield. So let's go downfield. And it's 14.5 meters. Please don't sweat the lack of scale here. And what is the total displacement? Again, vector, which means I need magnitude and direction. So I'll be using the Pythagorean theorem and the inverse tangent function. Okay, so we have this resultant, again, represented by D, that represents kind of like a straight line displacement. So, again, the ball traveled first, again, east or across the field, and then north or up the field. And so the angle that we're going, the angle that we're going to represent is this angle right here. Okay, so first we're going to use the Pythagorean theorem. Again, Pythagorean theorem says that the magnitude of the resultant is going to be equal to the square root of delta x squared plus delta y squared. And then if I actually plug in my values, I'll end up with 6.0 meters. I'm looking at the wrong thing. And I'm going to square that. And then 14.5 meters, again, squaring that. That is all square rooted. Now, I'll actually square some numbers here. So I'll have 36. I'm going to stick with 2 sig figs here. 36 meters squared plus, and then we're going to have a little bit of a tricky time here, because if I were to actually square this number and represent all of the significant digits, I would, all the placeholders, I would use too many significant figures. If I wrote out the entire number, again, if you're just trying to do your work, that's totally fine, totally legit. You'd have to take them into consideration when you selected your final answer. That's totally legit. But right now, I'm actually going to represent this intermediate step with the appropriate number of significant figures by writing this in scientific notation. So 2.10 times 10 to the second meters squared. Okay, so that's going to be 210. Or you could just write 210 with a decimal. That's all fine. It's all great. Now, this is all square rooted. Don't forget about that. And so this ends up being 246 meters squared when I add it together. And that becomes, when I actually square root it, 15.7 meters. So my magnitude is 15.7 meters. All right, so we have our magnitude. Now we need our direction. So our angle is going to be the inverse tangent function. Again, opposite over adjacent. So let's see. X delta y. This would be a little bit backwards. We're going to go which ends up being 22 degrees. And however you want to say this change of direction, I do not care. How about to the side of downfield? Again, I do not care how you explain that direction, as long as you have something that is at least close to appropriate.